last lesson of the last unit of Physics 30. This is the current theory that we use to understand the atom. Okay, so up to this point, we know protons, neutrons, electrons. We have an idea how they orbit. But we keep having scientists do these experiments like the thin gold foil experiment, and alpha particles pass through. And as our ability to create instrumentation catches up with our theories, we get to go deeper and deeper. And it's exponentially faster and faster. Like when we first start talking about Dalton's billiard ball model, we're talking like the early 1900s. So we're not even 100 years out from that very first theory. And here we are, we're already discovering new subatomic particles beyond what the textbook already talks about. Okay? So we're looking at particles, and we call them quarks. There's bosons. You've heard of the Higgs boson. There's leptons. There's also snap, crackle, and pop. They're not just a Rice Krispie sound. They're subatomic. Okay? So as we get further into as our ability to create the instrumentation catches up, we get to go further and further. And so far, even with the level of technology that we have, we still can't disprove a lot of the theories that were set in the early 1900s. Okay? All right. So strong, if your force is strong nuclear force, that means it holds the nucleus and the quarks together. So this is at the nuclear size. If it's an electromagnetic force, it's the force of attraction. That didn't change between charged particles, and that's infinite. When we have weak nuclear force, it allows the transmutation of quarks in beta negative and beta positive nuclear reactions. So we've already looked at that. When we have a beta negative decay, we get a new daughter cell, an electron, and an antineutrino. If we have beta positive decay, we get a new daughter cell, we get a positron, which is essentially a positive electron, and a neutrino. Okay? And then if we're looking at gravitational forces, this is where we have the attraction of masses, and it's unlimited. Our force strength starts out here. This is the strongest force at nuclear, and we go down to gravitational, and this is the weakest. Okay? And it makes sense, and it puts the strength of force into perspective. We need those gravitational forces in play to keep our moon where it's at in relation to Earth, because it controls our tides, which controls our weather. And that's a pretty relatively strong force, but yet it takes that much more force to keep the nucleus of our atoms the way that they are. Okay? So, physicists have been able to break neutrons and protons down into small subatomic particles, and what was happening was they needed large amounts of energy to overcome this strong force. So, particle physicists will collide atoms with each other, and this is in the Hadron Collider in Switzerland. This is a massive, massive piece of equipment. Okay? So they were able to break the atom down into subatomic particles, but they needed a way to detect those particles, and so they used bubble and cloud chambers that track the path. This is where the concepts get a little, you just got to have an open mind. All right, so cloud chamber is a dust-free supersaturated vapor from a liquid such as water or ethanol, and a bubble chamber contains a liquefied gas just on the verge of boiling. So it could even be like, it wouldn't be, but it could be like liquid propane. Propane is a liquid under pressure, and just as it's being introduced or the pressure is being released, it sublimates and it goes into a gas. But right before it goes to a gas, there is that point of boiling, and that's what they're trying to hit. So a charged particle speeds through the cloud chamber, and it will either cause the vapor to condense into droplets or cause the gas in the bubble chamber to vaporize into gas bubbles. So it leaves behind a trail. And so neutral particles, you have to be either positive or negative. Neutral particles don't. So what this picture shows is this cloud, and you can't see it very well, but it will swirl around like this. There's little swirly marks in here. Okay, it'll go in a circular pattern. An external magnet field is applied, causing the charged particle to move in a circular path, which helps them determine what type of particle set that path. So let's just look at these pictures. If we had a scenario where we had our magnetic field going in which direction? Which direction? This magnetic field. The point of the arrow is coming at you. So this isn't into the page. Into the page would be the tail feathers. This is out of the page. Okay? So if I had a proton, which hand am I going to use? Right hand. So the magnetic field is out of the page. Okay? If I had a proton and it was going here, and my magnetic field was going in out of the page, which way is that proton going to be forced? Down. Okay? So this is a proton.
Is it always like
Yeah. Either way, it's going to be forced this way. Right? Like if you had the paper like this, it would be forced down. If you have the paper like this, it's still going to force it this way towards you, right? So it's still going to be this way. Yeah. I know it's a hard thing to visualize, and I'm probably not the best person to help you visualize that because I leave my paper flat. Yeah. Okay. All right. If I had an electron, let's make him blue. If I had an electron, what hand am I going to use? Left. Okay, so it's coming out of the page and it's coming out of the page and it's going this way. Which way is the electron going to go? Up. Your palm was facing that way, right? Yeah. He's doing it like this, you're doing it towards you. It's the same, you're doing the same thing.
Oh, is it not the palm?
Yeah, it's the palm.
Oh, yeah.
It is the palm. You and I were doing it one dimensional way. Daniel is doing it in a in a 3D dimensional way. It's fine. Yeah. He's doing it like this, that it's coming literally out of the page like this, and the electron's moving this way, so it's going to curl up this way. Daniel's physically doing it in 3 dimensions. You and I are doing it in 2 dimensions, and that's what Avery was just asking. Okay? So this is an electron. Okay? What would a positron do? We need to remember what a positron is. It's a positive electron. So it's going to behave like a proton. Okay? So that's a positron. Now, if I increase the speed of that electron, what do you think would happen to that curve? It would go further out, yeah. Okay? So we need to make sure when we're doing this that we're doing our third left-hand rule, because we need electron direction. We need north-south, not north-south. We need magnetic field direction. And we need force magnetic direction. That's the third left-hand rule. Okay, when we look at these paths, we can see that they're what shape? Or going to do what shape? What shape does this look like it's going to do? A circle. So when we're looking at circular motion, we know that force centripetal can be equal to force magnetic. Okay? Force centripetal being mv squared over r, that's our radius, and magnetic being qvb. Okay? And so we can say that mv squared is equal to qvbr. However, we're smart enough to understand that this velocity will take out one of those velocities. So m is equal to m is equal to qbr. mv is equal to qbr. If I was to isolate and look at the relationship between radius and mass, what could we say? What kind of relationship would it be? We have 2 to choose from, proportional or inverse. It would be directly proportional. What about velocity and radius? So as my mass goes up, my radius will go up. And as my velocity goes up here, my radius will go up. Okay, so 3 subatomic particles. What that aren't going to leave a track? What's the main one that we just saw? Neutron. And then we learned 2 words when we learned beta decay, positive and negative. We get a daughter cell, we get an electron, and we get a antineutrino. And in beta positive decay, we get a daughter cell, a positron, and a neutrino. So any, if we look, neutral, neutral, neutral. Okay, any neutral particle. So it says here in number 3, describe and explain the differences in the track marks made in a bubble chamber by the particles in each pair, protons and alpha particles. So if I'm looking at a proton and an alpha particle, what do we know about their charges? No, I don't need the number, but what do we know about them? They're positives. Okay, so if we were looking at a proton and a positron, what pathway did they take? They took the same pathway, right? So protons and alpha particles are going to have the same direction. Okay, and when we look at mass in relation to radius, which is larger, a proton or an alpha particle? An alpha particle at 6.65 times 10 to the negative 27 kilograms, whereas a proton is only 1.67 times 10 to the negative 27. So the alpha particle will have a larger radius. Okay? So the charge is 2 times larger, right? The charge on a proton versus the charge on a alpha particle. This is 1.6 and this is 3.2. So the alpha particle is 2 times larger. And when we look here at the mass, what do we see? What do we see in relation to each other? The alpha particle is 4 times larger. Okay? So it's definitely going to have a much larger radius. Oh, absolutely. Probably need to see that, hey? Okay, what about a proton versus an electron? What kind of curvatures are they going to have? In the same direction? Different direction, okay? Because one's positive versus one being negative. Okay, which one between the two will have a larger radius? Yep, because why? Okay, so this one here is A, this one here is B. So proton and electron, they're going to have opposite pathways in a bubble chamber. And the proton is going to make a larger pathway than the electron because it has a larger mass. And we know that mass is proportional to radius. So as I increase my mass, I'm going to increase my radius. And when we go all the way back to centripetal force, think about it when you're on a ride that goes in a circular motion. those, especially the ones that you know where you sit on it and they spin you backwards to music and you go up and down but in a circle, you want to be the big guy on the outside and not the little guy, because the little guy is going to get crushed. The larger mass has the larger radius. That mass wants to go to the outside. Okay? We learned the hard way because my mom stuck us on the outside and then she sat on the inside when we were little. Okay, subatomic particles is quark. That was at the time the smallest subatomic particle. We've since learned smaller ones. Okay, quarks have fractional charges. So we've gone this whole time where everybody has to have this lovely whole number. Now we get fractional charges. But they work together to create that whole charge. So on your data sheet, here, it will tell you, bottom left, it tells you an up quark is 2/3 of an electron, an anti-up quark is a negative 2/3 of an electron, a down quark is a negative 1/3, and an anti-down quark is positive 1/3. So pay attention because the signs don't line up. Like, don't think up is positive and anti is negative. So up quark is positive and an anti-down quark or anti-quark is positive. So an anti-down and an anti-quark is positive. An anti-up anti-quark is negative and a down quark is negative. Okay? So it's keeping everything straight. All right. So combination of quarks make up protons and neutrons. Stable matter such as neutrons can only be composed of up and down quarks, no antimatter. This is key when you're building things. Stable matter such as neutrons and protons can only be made up of up and down quarks, not anti-up antiquarks and not anti-down antiquarks. Unstable matter has to have at least one antiquark. So if I was to look at quark composition of a proton has what charge? Positive. So I have positive 1. And it says that protons need to be made up of no antimatter. So it can't have any anti-up or anti-down quarks. So if you look here, an anti-up is a U with a line over it, and an anti-down is a U with a D with a line over it. So we're not going to have those in a proton or a neutron. So it's going to be made up of and when we look, an up quark is 2/3 and 2/3, and a down quark is negative 1/3. You need 3. 3 particles make up the matter of a proton or the matter of a neutron. Okay? So an up, up, down. A neutron has a 0 charge. It's neutral. So it's going to have 3 as well. Again, it can't have an anti-up or an anti-down quark. So how are we going to get to 1 with a combination of 2/3 and negative 1/3? If I start with 1 up, I'm at 2/3. I can't use anti-up or anti-down, so I'm going to use a down quark. If I use 1 down quark, now I'm at 1/3. And if I use another down quark, I'm going to use another 1/3. Okay? So they're always in groups of 3. Okay. When we look at beta negative decay, let's start with a neutron. What is the A and Z values for a neutron? 1 and 0. Okay. Okay. What do we get from our parent cell? We get a daughter cell. And in this particular case, we get a proton. We get our electron. And we get a antineutrino. What about beta positive decay? I'm going to start with my proton. And my daughter cells are going to be, what do you think your daughter cell is? This is a neutron, gives me a proton. So here I have a proton. It's going to give me a neutron. My positron and a neutrino. Okay. If I was to code this with quarks, I would have an up, down, down is going to give me an up, up, down, plus an electron, plus an antineutrino. How would I code beta positive decay? What does a proton look like? Up, up, down is going to give me up, down, down, plus a positron, plus a neutrino. Okay, so let's look at page 339, 1 to 4, and 6 to 11 and 14. Let's start there.